It is late November 1944, somewhere along the hardened edge of the German frontier. A company of veteran Panzer Grenadiers moves cautiously across a frozen, snow-dusted clearing. 3 minutes, while the unseen enemy forward observer reads his map, calculates the error, and tells his guns to adjust. The Grasshopper could look behind ridgelines, over forests, and deep into enemy staging areas. To German armor commanders, the sight of the slow-moving little plane was deeply unnerving. It meant they had been spotted by the network. Together, the thousands of miles of copper wire, the hand-cranked telephones, the backpack radios, and the aerial observers formed a robust, overlapping grid. A 22-year-old lieutenant pinned down in a frozen ditch possessed the same immediate communication capability as an observer soaring 3,000 feet above the battlefield. They could bypass the slow, traditional chain of command and speak directly to the Fire Direction Center with the clarity of a civilian making a telephone call in New York City. The physical infrastructure had been successfully laid. The military had built the communication backbone required to link a single pair of binoculars to dozens of heavy cannons. But moving a voice across miles of contested terrain was only half the operational equation. Delivering a grid coordinate to the rear did not automatically fire a weapon. Once that panicked voice cracked over the loudspeaker inside the canvas tent, a different kind of machinery had to engage. The raw information had to be instantly translated into physical geometry. To unleash the devastating synchronized strike seen in the frozen clearing, the clerks inside the center had to process that single voice into specific firing data for multiple batteries separated by miles of terrain, and they had to do it faster than the enemy could run. But today, the sky remains silent. No spotting round falls. There is no whistle, no plume of dirt, no warning of any kind. When the radio crackled inside the Fire Direction Center, the men waiting at the folding tables did not panic. They functioned like actuaries in a high-stakes accounting firm. The tent often smelled of canvas, damp wool, and cigarette smoke, deliberately insulated from the immediate terror of the front line. A radio operator simply transcribed the incoming coordinate from the observer onto a paper slip and handed it to the fire direction officer. There was no debate about the tactical situation. The observer in the mud was the eyes. The men in the tent were the brain. The centerpiece of this operation was the plotting board. This was a flat wooden table covered with a standardized gridded map of the battlefield. The moment the coordinate arrived, a clerk placed a colored pin into the map at that exact location. This single point represented the target, the exposed infantryman frozen in the clearing. Already pressed into the board were other pins, permanently marking the surveyed locations of the American artillery batteries. Because the military deployed thousands of cannons, these batteries were scattered widely across the landscape. One group of howitzers might be dug into a reverse slope 2 miles to the south. Another battery of heavier 155mm guns might be hidden in a ruined village 5 miles to the west. The company reaches the center of the 400-yard clearing. They are completely exposed, but their experience tells them they are safe. Consequently, every single battery had a completely different geometric relationship to the newly pinned target. To bring all these weapons to bear on a single point, a specialized team of enlisted men, known as computers, went to work. They did not rely on slow algebraic equations. They used physical tools designed for speed. They placed a heavy, transparent plastic protractor over the target pin and pulled a string across the map to the pins representing the individual gun batteries. With a single motion, this tool measured both the exact distance in yards and the deflection angle for each specific cannon position. But map distance alone does not steer a heavy explosive. The computers cross-referenced this raw yardage with graphical firing tables. These were complex, custom-made slide rules that contained the exact ballistic flight data for different weights of ammunition. The computers slid the ruler to the target distance, then rapidly applied micro-adjustments. They compensated for the current barometric pressure. They factored in the wind speed aloft. They even adjusted for the temperature of the gunpowder, knowing a cold propellant charge burns slower and throws a shell slightly shorter than a warm one. In less than 60 seconds, the physical distance on the plotting board was converted into precise elevation and traverse numbers for the cannons. Telephone operators sitting at the edge of the tent instantly read these numbers over the wire directly to the gun lines. The rules of war dictate that sudden annihilation is impossible without a precursor. Without a single prior sound, the atmosphere shatters. The gunners standing beside the heavy artillery pieces did not need to know what they were shooting at. They simply turned their dials to the called-out numbers, locked the heavy steel carriages into place, and loaded the breeches. The mathematical architecture of the strike was complete. The FDC could rapidly plot a single target for a dozen different batteries, ensuring every barrel in the sector was aimed at the exact same patch of frost. But pointing the guns correctly only guaranteed accuracy. It did not explain the devastating shock of the opening scene. If a battery 2 miles away fired at the exact same moment as a battery 5 miles away, their shells would travel different distances and arrive at different times. The target would experience a scattered, rolling trickle of explosions, giving the surviving veterans ample time to dive for cover, to achieve a single deafening clap of instantaneous annihilation. The clerks in the tent had to manipulate something far more difficult than geometry. They had to manipulate time. The standard method of coordinating artillery was to synchronize the launch. A commander would simply order all his guns to fire on a single radio command. But because the cannons were spread across different distances, the shells spent varying amounts of time in the air. It is not the scattered, rolling thunder of a typical bombardment. It is a single, deafening clap of violence. The resulting impacts rolled across the target in a chaotic sequence. For the veteran infantryman, that first distant explosion was just as effective as a spotting round. It was the signal to dive for a trench. The architects at Fort Sill wanted to eliminate that warning entirely. To do this, they reversed the physics of the barrage. They stopped coordinating when the guns fired and began coordinating when the shells landed. This doctrine was called time on target. The execution of a time on target, or TOT mission, required absolute mechanical synchronization. Once the clerks in the Fire Direction Center calculated the geometry for multiple batteries, the Fire Direction Officer chose an arbitrary moment in the immediate future for the destruction to arrive. He would pick a precise minute and second. The center then broadcast a time check over the radio network. Miles apart from one another, officers standing in snow-filled gun pits pulled out their pocket watches. On the command of the FDC, they synchronized their sweeping second hands to the exact same tick. With the clocks aligned, the clerks consulted their graphical firing tables one last time. They looked past the elevation angles and found a specific column for time of flight. The physics were unyielding. A heavy 155mm shell fired from a battery 5 miles away might require 38 seconds to complete its parabolic arc. Dozens of high-explosive artillery shells materialize out of the overcast sky and detonate at the exact same fraction of a second. A lighter 105mm shell fired from a forward position only 2 miles away might take just 14 seconds to reach the same patch of earth. To make them land together, they had to be fired apart. The FDC radioed the specific flight times to the individual batteries, along with the designated impact time. From that moment, the entire network went silent. The battery commanders stood beside their loaded cannons, staring at their synchronized watches, counting down the seconds backward. The battery furthest away acted first, At exactly 38 seconds before the impact time, the commander dropped his arm. The lanyards were pulled. The heavy guns roared, sending their steel projectiles climbing into the overcast sky. For 24 seconds, the closer battery did nothing. The men simply waited, while the distant shells flew miles overhead. Then, at exactly 14 seconds before the impact time, their commander gave the order. The closer guns fired, sending their own lighter shells chasing after the heavier ones, high above the frozen European landscape. A complex mechanical ballet was unfolding. It was entirely silent to the men walking on the ground. Dozens of high-explosive projectiles, traveling at supersonic speeds from entirely different compass directions and altitudes, were converging on a single set of map coordinates. Perfectly blanketing the clearing, the ground heaves upward. Steel shrapnel shreds the freezing air, turning the open space into a corridor of instantly expanding shockwaves and torn earth. They descended through the freezing air in a synchronized swarm. This is what shattered the veteran infantrymen in the opening clearing. The atmosphere did not tear apart gradually. Because the FDC had perfectly staggered the launch times, the 38-second shells and the 14-second shells reached the frozen mud at the exact same fraction of a second. The combined detonations multiplied the concussive force, creating a localized earthquake that left absolutely no time for human reaction. The math had worked. But executing a flawless calculation under controlled conditions was only a baseline. The system performed perfectly against a single exposed company. The question was whether this invisible machinery of wire, radios, and synchronized watches could hold together when subjected to the crushing operational pressure of a massive enemy offensive. In the pre-dawn darkness of the 16th of December 1944, the theoretical perfection of the Fire Direction Center faced its ultimate test. The German military launched a massive, desperate offensive through the freezing, snow-choked forests of the Ardennes. The conditions were specifically chosen to blind the Allied war machine. Thick winter fog immediately grounded the slow-moving L-4 grasshoppers. Opening artillery barrages shredded thousands of miles of copper wire. The blast radius of the combined detonations leaves no dead space to hide in. The veteran infantrymen are caught completely upright. Advancing panzer columns overran forward observation posts, bypassing infantry and forcing American artillery batteries into sudden, chaotic retreats along muddy logging roads. Under this crushing operational pressure, a rigid, decentralized command structure would have shattered. If guns were tied directly to specific infantry units, those guns would have been rendered useless the moment the physical line was cut. But the American artillery network was designed to survive friction. When the heavy canvas field telephones went dead, the portable backpack radios simply took over the load. When a trained artillery observer was killed, an infantry sergeant picked up the handset, read the map, and transmitted the coordinate. And because the individual cannons were mathematically linked to a central brain rather than physically tethered to a specific trench, a retreating battery could drop its trails in a new clearing, rapidly resurvey its position on the map, and instantly plug back into the lethality of the grid. The true scale of the system revealed itself along the northern shoulder of the offensive, near the Elsenborn Ridge. German infantry and heavy armor massed in the dense woods, preparing to smash through the thinly stretched American defensive lines. They formed up under the cover of darkness, confident that the bad weather and the chaos of the offensive had blinded their enemy. Their instincts are rendered useless because the mechanism they relied on to survive has been entirely bypassed. But a lone American observer, freezing in a forward foxhole, spotted the staging area. He keyed his radio and transmitted the coordinate. He did not ask for the support of a single battery. He relayed the target to the division FDC, which instantly recognized the severity of the armored threat and patched the coordinates straight up to the corps-level artillery network. Inside multiple canvas tents spread across the rear echelon, clerks rapidly plotted the geometry for a target they could not see. They pulled firing data for standard 105mm howitzers, heavier 155mm guns, and massive 8-inch siege cannons. They calculated the flight times, issued the time check, and passed the command to the gun lines. Across a dozen different mud-choked clearings, artillerymen synchronized their watches in the freezing rain and began the staggered countdown. When the German assault forces stepped out of the tree line, they were not met by the standard, rolling drumbeat of a ranging attack. They were hit by a corps-level time-on-target barrage. Hundreds of heavy projectiles, launched from completely different sectors of the winter landscape, crossed the final distance in the exact same second. The coordinated impact broke the back of the assault before the panzers even crossed the line of departure. When the smoke finally clears minutes later, the clearing is devastated. The half-track is burning. The disciplined formation has been broken apart. The armor was immobilized. The infantry was scattered. The attack stalled permanently, shattered by guns they never saw, directed by a single man shivering in a hole. The surviving German commanders were highly trained professionals. They understood exactly what had happened to their staging areas. They could inspect the craters and calculate the sheer volume of high explosives that had materialized out of the fog without a single warning shot. They recognized the absolute tactical supremacy of a synchronized strike. But witnessing the terrifying consequences of the American fire plan only raised a more profound problem. The Axis officers could clearly see the result of the time-on-target doctrine. The question was why, even after suffering through it, they were utterly incapable of copying it. The German commanders who survived the avalanche of steel in the Ardennes were not ignorant. They possessed some of the finest artillery officers in the world. They understood the mathematics of indirect fire, and they immediately grasped the tactical genius of the time-on-target barrage. The concept itself was not a heavily guarded secret. It was merely a different application of time and geometry. But understanding the American system was entirely different from replicating it. The barrier to entry was not intellectual, it was industrial. The temperature is hovering just below freezing. The only sounds are the rhythmic crunch of boots on hardened mud. To the survivors, this event makes no logical sense. Artillery batteries are physical machines operated by human beings. To copy the fire direction center, an opposing army could not simply rewrite its field manuals. It had to possess a manufacturing base capable of producing absolute uniformity on a continental scale. The American artillery network functioned only because it was built on a foundation of limitless, standardized materials. The most critical component was the radio. A centralized brain requires constant, stable communication. The American backpack radios utilized frequency modulation, which provided clear voice transmission through the static of a chaotic battlefield. But building these radios required perfectly cut quartz crystals to stabilize the frequencies. The United States industrial base mined, cut, and distributed millions of these crystals, allowing the military to put a reliable radio on the back of nearly every forward observer and infantry platoon leader. The Axis powers, starved of raw materials and precision manufacturing capacity, simply could not replicate this vast web of wireless communication. They remained heavily reliant on vulnerable telephone wire and visual signals. When their physical cables were cut, their guns went blind. The second barrier was the ammunition itself. Time on target requires absolute ballistic predictability. If a battery is commanded to fire a shell, with exactly a 38-second flight time, the propellant must burn at the exact expected rate, and the fuse must detonate at the precise fraction of a second. A standard battery of 105mm howitzers stationed miles away cannot simply guess a precise grid coordinate on the first try. The American factories achieved a level of mass-produced standardization that ensured a high-explosive shell manufactured in Detroit behaved exactly like a shell manufactured in Philadelphia. If enemy ammunition batches varied slightly due to late-war chemical shortages or compromised propellants, their flight times would drift. A barrage meant to arrive in unison would stagger and scatter, entirely ruining the sudden shock effect. Finally, there was the sheer weight of logistics. Centralizing artillery meant constantly moving heavy command tents, specialized plotting equipment, and thousands of miles of heavy copper wire to keep pace with the advancing infantry. The American army was completely motorized, utilizing an endless supply of reliable transport trucks. The German army, despite its fearsome frontline armor, still relied heavily on horse-drawn transport for its artillery pieces and supply wagons. A horse-drawn battery cannot rapidly displace through freezing mud, resurvey its position on a map, and instantly plug back into a centralized electronic grid. The enemy could not simply copy the American tactic, because the tactic was not just an idea on paper, it was the physical manifestation of an untouched industrial empire. The time-on-target barrage was the deadly, visible edge of a logistical supply chain that stretched all the way back across the Atlantic Ocean. Yet, characterizing this overwhelming advantage purely as an industrial machine ignores the reality on the ground. A radio does not carry itself through a shattered forest. A copper wire does not string itself across a contested river. They cannot hit a moving target in a random field without a forward observer calling out ranging adjustments. The vast mechanical brain of the American artillery network may have been forged in safe factories, but maintaining that mathematical advantage on the freezing battlefields of Europe required constant, unseen human labor. The veteran Panzer Grenadiers who lay scattered across the frozen clearing in the opening moments of this story did not die because they were careless. They died because they trusted the established laws of warfare. They listened for the familiar warning of a single spotting round, completely unaware that the mathematics of survival had been rewritten miles behind the front line. The sudden, synchronized violence that broke their formation was not an accident, and it was not a miracle weapon. It was the lethal culmination of an invisible, continent-spanning machine. The question was never really about how a single observer could summon a rain of high explosives out of an empty sky. It was about how an entire military force reorganized its operational mind. The time-on-target barrage proved that the deadliest weapon on the battlefield was not the physical cannon itself. It was the communication network that linked the cannons together. The Americans had successfully turned thousands of isolated, blind artillery pieces into a single, devastating shotgun, aimed and fired by a centralized brain. Yet, someone had just dropped the combined firepower of multiple heavy batteries squarely onto a small patch of frost. But that brain was not an unfeeling, automated machine. The theoretical elegance designed in the classrooms of Fort Sill survived the freezing mud of Europe only because human beings absorbed the friction. To keep the math perfect, men had to endure absolute exhaustion. Inside the fire direction centers, clerks worked staggering, sleepless shifts in damp canvas tents, their hands numb from the cold. They slid plastic protractors across paper maps by the dim light of kerosene lanterns, acutely aware that a single mathematical error, a slight miscalculation in wind speed, or a misplaced decimal in a flight time would drop a barrage of heavy steel directly onto their own advancing infantry. At the gun lines, artillerymen stood in ankle-deep, freezing water. They did not just fire the weapons, they fed the system with pure physical labor. They manhandled 90-pound projectiles into heavy steel breaches hour after hour, permanently deafened by the concussive roar of the batteries. trusting the disembodied voice on the field telephone to tell them precisely when to pull the lanyard. And, holding this entire terrifying architecture together, were the most vulnerable men in the theater. The system relied entirely on radiomen, carrying 35-pound transmitters on their backs, their long antennas drawing deliberate sniper fire with every step, perfectly on time and perfectly on target, without a single test shot. The men bleeding in the snow assumed they were simply unlucky. It depended on the linemen, the unseen laborers of the network, who crawled through shattered timber and fresh artillery craters. They spooled heavy black copper wire through their bare hands, searching for severed connections in the dark, splicing the lines, with frozen fingers under active mortar fire, just so a panicked coordinate could reach the rear. The infantrymen caught in the clearing never saw any of this. They never saw the factories in Detroit, the clerks doing geometry in the tents, or the linemen bleeding in the mud. They only looked up at a silent sky. All of that immense industrial power, all of that mathematical genius, and all of that human suffering was ultimately funneled down into a single point of execution. It all rested on a young soldier shivering in a forward foxhole, watching the enemy through a pair of cold binoculars, pressing a rubber button on a handset, and quietly speaking a string of numbers into the winter air, caught in an accidental 0 point of some massive, blind bombardment. They cannot see the lone American soldier sitting 2 miles away on a wooded ridge, holding a black rubber radio handset. He has no heavy weapons of his own. He did not fire a flare. He merely looked through his binoculars, read a map coordinate, whispered a few numbers into the microphone, and waited. This lone observer had triggered a localized apocalypse. But to understand how a single voice could summon such immediate, pinpoint destruction without warning, we first have to understand why the victims believed they were safe. We have to examine the rigid, mathematical laws of gunnery, the metallic rattle of equipment, and the low idling of a half-track engine keeping pace in the rear. These are experienced soldiers that both sides trusted, and why the old way of dropping steel on a target made this sudden nightmare seem physically impossible. Firing a heavy artillery shell is an exercise in applied physics. A standard American 105mm howitzer lobs a 33-pound projectile across several miles of curved airspace. Once the shell leaves the barrel, it is entirely at the mercy of gravity, atmospheric pressure, wind speed, air temperature, and even the rotational spin of the Earth. Because the gunners are stationed miles behind the front lines, tucked behind hills, or inside dense forests, they cannot see what they are shooting at. They are firing blind, relying entirely on a forward observer near the front line to act as their eyes. In the traditional doctrine of the First World War and the early years of the Second, this relationship was rigid. An observer was mechanically and doctrinally tethered to a single, specific battery of 4 to 6 guns. When he spotted an enemy formation, he consulted his map, estimated the distance, and radioed or telephoned a grid coordinate to his battery. But the observer was human. His initial coordinate was almost always an educated guess. He could not perfectly account for the exact wear on the howitzer barrels or the shifting wind currents miles away. Therefore, the guns could not simply unleash their full payload. They have survived the Eastern Front and the long retreat across France. They know exactly how to stay alive. They had to test the math. The battery would fire a single spotting round. The observer would watch the horizon, wait for the grey plume of dirt, and measure the error. If the shell landed 200 yards past the target and 50 yards to the left, he would transmit a correction. The battery would adjust the elevation and traverse of the gun tubes and fire a second round. This process of bracketing the target continued until a shell landed exactly where the observer wanted it. Only then would he issue the command to fire for effect, unleashing the rest of the ammunition. This ritual of ranging in took time. It took minutes of back-and-forth communication and manual calculation at the gun line. For the infantrymen on the receiving end, whether they were German, Soviet, British, or American, this delay was a recognized lifeline. The first spotting round was an alarm bell. It announced that they were seen, that a mathematical formula was being written about their exact location, and that they had a few precious minutes to dig a hole, find a stone wall, or sprint into the timber. This was the universal law of indirect fire. It was predictable because it was decentralized. If an observer wanted to hit a target, they scanned the tree line, maintaining a disciplined 20-yard interval between squads. Most importantly, they are listening to the sky. With more than just his own 4 guns, he had to pass the request up a slow chain of command, where it would be routed to other batteries, who would then have to begin their own slow, individual bracketing processes to find the range. The veteran infantrymen in the frozen clearing were operating under this exact logic. Their expectation of safety was not arrogance. It was a rational belief in the mechanical limitations of their enemy. No spotting round meant no math had been done. Yet, the devastating strike that hit them proved otherwise. Dozens of guns, positioned in different geographic locations, had fired at the exact same coordinates simultaneously, landing perfectly on the first try. The lone observer on the ridge had bypassed the rigid laws of bracketing entirely. To understand how he achieved this, we must look away from the freezing European battlefield and return to a quiet peacetime classroom in Oklahoma, where the United States Army decided to quietly steal the mathematics of gunnery away from the men on the front line. The answer began years earlier, far from the freezing mud of the European theater. It started on the dusty, sun-baked plains of Oklahoma during the 1930s. At the United States Army Field Artillery School at Fort Sill, instructors were studying the static, bloody artillery battles of the First World War. To a veteran infantryman, artillery is a predictable enemy. It follows strict mathematical rules. Before a heavy barrage can wipe out a moving formation, they recognized a fatal flaw in how armies dropped high explosives on their enemies. The next war would be mechanized. It would move too fast for commanders to spend days surveying gun positions and running telephone cables to fix trenches. The fundamental problem was cognitive overload. Under the old doctrine, the forward observer was being asked to be both a scout and a mathematician. A man pinned behind a shattered wall under machine gun fire, shivering from the cold, cannot reliably calculate air density, propellant temperature, and complex trajectory curves. If his math was wrong, the shells missed. If his math took too long, the enemy simply drove away. The instructors at Fort Sill realized the solution was a quiet, bureaucratic revolution. They decided to sever the intellectual link between the man seeing the target and the men firing the guns. They stripped the calculation duties away from the terrified observer on the front line and moved them to a centralized location. They created an entirely new node in the chain of command, the Fire Direction Center. The FDC was not a weapon system. It was a canvas tent erected a few miles behind the fighting, filled with folding tables, standardized maps, and clerks holding pencils. Under the new doctrine, the forward observer no longer told the guns how to shoot. He no longer calculated elevation or traverse angles. The enemy must first find it. That means a single spotting round. A lone shell will whistle overhead and detonate, kicking up a plume of grey dirt. He simply reported what he saw. He would look through his binoculars, read a map grid, and send a raw target coordinate backward into the rear. Inside the FDC tent, the real weapon took shape. A specialized team of men received the observer's raw coordinate and pinned it on a master map. Because they were sitting in a quiet, relatively safe environment, they could perform complex calculations rapidly. They used graphical firing tables, which were specialized rulers that instantly converted map distance into the exact barrel elevation required for the howitzers. They factored in the wind speed aloft. They adjusted for the temperature of the gunpowder. They even calculated the specific microscopic wear inside the steel barrel of each individual cannon. This centralization changed the fundamental architecture of the battlefield. The observer on the ridge no longer owned a single, dedicated battery of guns. The FDC owned them all. If the observer reported a single machine gun nest, the men in the tent could assign 4 guns to handle it. If he reported an entire mechanized infantry company exposed in a frozen clearing, the FDC could instantly route the firing data to 3, 4, or 5 different artillery battalions spread across miles of terrain. The individual cannons were no longer independent actors. That is the warning. When that single shell lands, the men on the ground know they have precisely 3 to 4 minutes. They had become muscles taking orders from a single, centralized brain. This is why the spotting round was disappearing. The observer did not need to fire a test shot to correct his own panicked calculations, because the calm men in the tent had already perfected the geometry on paper. The mathematical guesswork had been eliminated before the breech was ever loaded. It was a brilliant theoretical concept, but an idea drafted on a chalkboard at Fort Sill is not a weapon. A centralized brain is useless if it cannot communicate with its muscles. To survive the extreme friction of a moving war, to synchronize dozens of guns across ruined towns and dense forests, the American army had to physically wire the battlefield together. To make a centralized brain function, it must have a nervous system. In the European theater, that nervous system was unspooled by hand, mile by mile, through freezing rain and shattered forests. The United States Army recognized that the Fire Direction Center would be entirely deaf without absolute, uninterrupted communication. To solve this, they blanketed the battlefield in assault wire. It was a thin cord of copper and steel strands wrapped in rubber, carried on heavy metal spools by linemen who crawled through mud and climbed shattered trees under enemy fire. 3 minutes to dive into a trench, scramble behind a stone wall, or sprint into the thick timber. At the front line, the observer connected this wire to an EE-8 field telephone, housed in a heavy canvas or leather case. The device required the operator to crank a small handle to generate a ringing current. When the connection was solid, it provided clear, instantaneous voice communication directly to the artillery battalions in the rear. It was secure and reliable, but war rapidly destroys physical infrastructure. Artillery barrages shredded the lines. Advancing Allied tanks inadvertently crushed the wires deep into the dirt. The centralized system needed redundancy to survive, the friction of combat. The answer came through a massive manufacturing base, which flooded the theater with frequency-modulated portable radios. When the telephone wire inevitably snapped, the observer simply reached for an SCR 300 backpack radio, weighing 35 pounds and carried by a dedicated radio man. This device allowed the observer to move freely with advancing infantry while maintaining a continuous link to the rear. He did not have to tap out Morse code. He simply pressed a switch and spoke into a handset. This invisible web of radio frequencies extended upward into the sky. The military deployed hundreds of L-4 grasshoppers, essentially civilian Piper Cub airplanes painted olive drab. They were unarmed, made of fabric and wood, and flew so slowly they could nearly hover into a strong headwind. But bolted behind the pilot was a heavy radio and an airborne observer.